Thanks for coming again. So I'm going to go slightly off what I said I would do this talk, because what I said I would do might take 6 hours, and this is maybe a 1.5 hour version of some piece of that 6-hour tutorial or 2-hour version. So what I'm going to talk about, I don't know if everyone came to my talk from 3 days ago, but I showed the results of optimization calculations of various simple and more complicated mechanical models. For instance, I showed the optimization calculation using a point mass model with a leg with a telescoping actuator. Everyone thinks this is a damper. This is not a damper. This is a telescoping actuator, which means that it can produce forces arbitrarily. And it produces some optimal gates that I showed last time that look like this. And then I briefly flash this more complicated model with muscles, with its own muscle properties, which can be made to do crazy things by appropriately actuating the muscles, giving it really weird force as functions of time. And then you can do an optimization calculation. And when you ask it to go slow, it does something like this. And when you ask it to walk on toes, it does something like that. Now, what do we mean by that? Like, how do we do these calculations? Is going to be the subject of today's tutorial or lecture, if you will. So the target audience, I would say, is basic familiarity with MATLAB. Who's not familiar with MATLAB? Or is everyone comfortable with MATLAB, or not really? Yes? No? Yes? Okay. What? Called MATLAB? Interesting. I wish I had a good rejoinder to that. No, I'm sure you're not. No, I believe you. Okay, so anyway, so that's what we'll do. And if you have MATLAB, that's great. There are also free optimization softwares. One is called SNOPT, and the student version is free, which can do optimization calculations for up to about 200 or 300 variables. I don't remember exactly, which is very good because SNOPT is actually better than MATLAB for optimization calculations. It's more robust, and the full version can solve vastly bigger problems more robustly, and so on. And actually, in my own research, that's what I use. Even though at least my smaller problems can be solved with MATLAB, but the bigger problems cries out for something better. All the programs that I will show in today's lecture, so I'll do a bunch of MATLAB demos as well, and if we have time, we can do exercises. But they're all available on my webpage. If you do something like this, you will get there. Maybe not all programs that I demo today will be on this zip file, because some of them were made after I did that. But if you ask me, I can send them to you, or I'll put it up on TEQP website. Okay. So, of course, this idea of trajectory optimization, in other words, trying to find the optimal trajectory of a mechanical system or some other system, is not specific to legged locomotion. Of course, that's just one example. You can list 20,000 examples, but here are some maybe prominent ones. You can design, for instance, trajectories to go to the moon or other planets. You have a rocket and you want to get from Earth to the moon with the least amount of fuel. That problem is basically the same as trying to going from here to there with the least amount of energy cost, except solving this problem is harder than solving that problem computationally, right? So this is an easy problem compared to the locomotion problem. And you can imagine a more detailed version of this sort of within the Earth, trying to optimize airplane plats and things like that. And this is what I've focused on most of my life, trying to figure out optimal trajectories or strategies for legged robots or animals. All kinds of mechanics problems, just classical mechanics problems, are secretly optimization problems. If you sort of did the dynamics courses, at least advanced dynamics courses, you would have learned about the principle of least action, where the Newton-Euler formulation of mechanics is shown to be equivalent to, in some sense, minimizing some object called action, which is a function of the state trajectories of the system. And all kinds of structural mechanics problems can be, at least static problems, can be thought of as potential energy minimization subject to various constraints. So those are also sort of are related to these. You can think of problems in design, of course, right? This is the classic situation in which we talk about optimization problems, and those are also very similar. They're all the same problem. So I joke that any problem can be turned into an optimization problem, and I only half joke because I think it's true. Okay, so what I will present is numerical methods, learning how to use MATLAB tools, and then how to set up these problems, and then I'll give a couple of examples of maybe 3 or 4 different examples of varying complexity, starting from a really simple made-up math problem to something that resembles motion. Maybe I'll actually show the program for doing the point mass model optimization calculation, and I'll upload it as well, and so on. Okay, so here's a made-up math problem, made-up optimization problem. I don't know if people can see in the back. Can people see? Yes? Okay. So this is f. F is a function of 5 scalar variables, x1 till x5, and it's a simple quadratic function. And what we would like to do is to minimize this function of 5 variables subject to these constraints. These constraints are, well, there are 2 equality constraints. This is a linear equality constraint. This is a nonlinear equality constraint. These 3 are inequality constraints. Right. So we have 5 unknowns. So you would call this a finite dimensional optimization problem. 5 unknowns, 5 constraints, 2 equality, 3 inequality, and some nonlinear function. And that made-up problem, so it's just made up, is an example of a more general optimization problem, which is remarkably general. A problem of the form minimize f of x, where f is some nonlinear function, and x is some, let's say, n vector, right, some bunch of n variables. And you want to minimize this function such that x satisfies a whole bunch of things, constraints. Of course, you can, okay, let me back up. A whole bunch of constraints. This is an inequality constraint. These are linear inequality constraint. A is some matrix, B is some constant matrix. This is a linear inequality. These are linear equality constraints. These are simple bound constraints. In other words, it says x1 should be maybe less than 5, greater than 0, or something like that, and so on and so forth. And these are nonlinear inequality constraints and nonlinear equality constraints. You might notice, let me see if I have, yeah, so this kind of problem is called a nonlinear programming problem or a nonlinear constraint optimization problem. And you might notice, by the way, that there is some redundancy in the description here. You could, for instance, simple bound constraints are just special cases of linear inequality constraints. In fact, linear equality constraints can also be written as 2 linear inequality constraints. If you say x equals 5, that can be rewritten as x greater than or equal to 5, and x less than or equal to 5. Those 2 inequality constraints imply x equals 5. So there is redundancy in this description, but it's nice to have these separate classes because sometimes some kinds of constraints, if you know the constraints are of a certain form, you can actually exploit that. Did someone have a question? No. Okay, anyway, so this is a general optimization problem, and MATLAB and many other softwares out there have ways of solving this class of problems. And fminCon is the MATLAB's version of the function that solves this class of problems, and it has these pieces. The first piece is the objective function, which in this case is f. X naught is the initial seed, in other words, the guess for what the optimum is, and A and A in EQ, B in EQ are the A and B in the inequality constraints, and these are the matrices in the equality, linear equality constraints. This is a lower bound, this is the upper bound of all the x's, and then a whole bunch of nonlinear constraints, and then some other stuff. Okay. These slides are also available to you, so you can take a look at it if you want later. So let's actually see how to solve this simple optimization problem. Let me go to MATLAB here. You see MATLAB, okay. So there are these two functions. I say obj underscore simple and cons underscore simple. The names of the functions are not important. This is the objective function. In other words, the function that you want to minimize, and it has one input, which I happen to call p input, which is really x in the in my slides, and p input has 5 pieces: x1, x2, x3, x4, x5. You unwrap it here, and then you evaluate the objective function, which is x1 squared plus x2 squared plus blah blah blah. Right. So this is just a function that evaluates the function, and the constraint. This is the function that evaluates the constraint, and again, p input is x1, x2, x3, x4, x5, and the output of this constraint function has 2 pieces. The first piece is the set of all inequality constraints, and the second piece is the set of all equality constraints, right? And so let me just point to this thing. This is the inequality, right? And what was it? Is x4 square plus x5 square minus 5, and by default it is assumed that this thing is less than or equal to 0. Okay, and this is x3 square plus x4 minus 2 equal to 0. Let's go back to right. So this is a transcription of these two, at least this inequality constraint and this function and so on. Okay, so those are all the functions that the nonlinear functions, and then there are these linear equality and inequality constraints. So here's where we call fmin_con, and it has as input the objective function, the constraint function here, and it has all these inputs, the matrices A in EQ, B EQ, A EQ, and so on, and those are constructed here based on what we want to solve, based on our constraints, right? So so AEQ is going to be 1, 1, 1, and the coefficient of x4 and x5 are 0. So AEQ is 1, 1, 1, 0, 0, and you will find that that's what it is here, and so on and so forth. You have the lower bounds. Only one of them has a lower bound, 0.3. Another one has an upper bound, 0.5. Everything else is bounded between 0 and infinity. So just give it infinity, right? So that's how you set it up, and then it's relatively straightforward. And you press play, and it finishes running, and that's it. It's already done. So that's a simple optimization problem. It doesn't matter what the solution is, but it seems satisfied. Okay. So that's the answer. Let's say we believe that that's the answer, and all constraints are satisfied. You can check if all constraints are satisfied by, of course, doing something like this. P result. CEQ satisfied to 10 to the minus 7, and C in EQ happens to be negative, so at least the constraints are reasonably satisfied. Okay, and you can check if P input is P result is every one of P input is less than or equal to every one of UB, which it is, right? So you do P result minus UB, everything is negative, so that's all good. And so on. You can check all the constraints. Okay, so that's a very simple optimization problem, and fmin_con enables it. And fmin_con is pretty good at solving these really simple constraint optimization problems. Of course, there are caveats. All right, so let's move on to here. I guess I'll leave it here. There are some caveats. So F-min-Con is what's called a second order method, which means that the method assumes that f is twice differentiable implicitly. It assumes that f and everything else that goes into this optimization problem, every function that goes into this optimization problem is twice differentiable. In other words, its gradient is continuous and its Hessian is also continuous. Hessian is the second derivative of a function, of a multivariate function. Okay. If these conditions are not satisfied, then you cannot trust the results. But sometimes it might still work. There is no guarantee that you will get the global minimum. The only guarantee, if the program works well and so on, if everything is good, you will get a local minimum, which might sometimes also be the global minimum. But it turns out this is a pretty good way to solve this class of optimization problems, and I basically use for all my calculations some variation of this class of methods. Okay. You can try to solve that problem if you want later. Okay, so let's do another baby optimization problem. We're just building up complexity, so this has some physics, some motion, and so on. So imagine that what you want to do is shoot a cannon and hit this target. So that's the problem. So it's a shooting problem, and you want to find the launch conditions to hit the target that minimizes the launch energy. Now, why would you want to minimize the launch energy? But maybe I want to attract Anindo's attention, but I don't want to injure him. So I want to throw something at him, but this is all I have, unfortunately. So I want to throw something at him, but I don't want to hit him too hard. So I want to minimize the energy of launch. Okay. So in any case, we want to transform this question into a nonlinear programming problem, shooting the target with minimum energy. Okay. One parameterization of this problem, right? So you want to go from a physical description or some description, verbal description of the problem to some mathematical representation of the problem, for which you have to choose a set of parameters that you want to use to represent the unknowns and so on. We'll talk more about this in a second, and there are lots of different choices, right? So in this case, I'm going to choose these three. I'm going to choose, strangely enough, the time of flight for this trajectory, and then I'm going to choose the initial x velocity, the initial y velocity. Those are the three things. You could also have a different parameterization, time of flight, initial velocity magnitude, and then the angle if you want, but we'll use the first parameterization. So how do you ensure that you hit the target? What you can do, now if you know those three numbers, the initial two velocities and then the total time, you can start it there. Let's say that's 0, 0, and this final point is given. Start it there, simulate it for the time of flight, and because you've sort of chosen these three quantities perhaps randomly, you will end up somewhere out here, and what you want to do is reduce the mismatch between these two things. So, right, so that's what you want to do. You want this point to be at this point. And essentially you can replace that condition that this point has to be the same as this point by a set of two constraints. The x position of this point is going to be vx times t, which should be equal to xt. So that's one constraint, and then there is another constraint for the y position as well. Right. So we have three unknown variables and two equality constraints. Now, in principle, you could, by doing some math, have turned this into an unconstrained optimization problem with just one variable. But just for fun, we are doing a three-variable optimization problem with two constraints. Okay, and the projectile energy is going to be vx squared plus vy squared. So that's maybe if you want to write it in a manner that looks slightly more mathematical, you can write it like this. This is what you want to minimize, two equality constraints, and then there are three inequality constraints. The inequality constraints for the velocities are trivial, so to speak. In other words, they're completely unbound. They could be completely unbounded. And then the time of flight, you say, has to be positive. You don't want it to be perhaps 0, because sometimes that causes problems. If you're integrating a differential equation, you don't want to be integrating for a zero mode of time. Not that there is anything wrong with that, but just that function evaluation might confuse the optimizer sometimes. So you want something that gives you reasonable answers. So let's make it small but not 0, and then leave it at that. Okay, so let's go to MATLAB again quickly. So again, we have these same functions: the objective function, the constraint function, and so on. The constraint function has these two inequality constraints here. Well, again, we are unwrapping p input. We are just computing the end position for a given p input, and then saying CEQ equals the computed end position minus the required end position. So those are going to be two equality constraints that are nonlinear, and then the objective function is just vx naught square plus vy naught square. Okay. Then you can run this thing, and then we embed the lower bound, upper bound, and so on. Run this thing. We had so I'm just for fun, I'm plotting the intermediate solutions as it searches for the correct answer. You notice that initially it's not far from satisfying the constraint, and then it now is pretty close to satisfying the constraint, and now it's just tweaking the kinetic energy so that it's minimum. It's stopped now, it looks like. So it seems happy. And then we can evaluate the probably we have more variables. The equality constraints are satisfied to 10 to the minus 7 again, and this is probably pretty close to the correct answer. Again, I'm not going to check it. I've checked it before that it is the right answer, to about 10 to the minus 7. Okay, so that's a simple example of a physical problem. Let's take a slightly more complicated physical problem. Now approaching perhaps a problem of the level that I described in my talk. Let's watch this video. Can people, is it too dark? Can people see what's going on in the back? Yes. So that's a, people are offended if you say monkey. It's an ape. I think it's some kind of a gibbon or chimpanzee. Maybe a chimpanzee. I forget. In any case, this video is from John Bertram, University of Calgary, who's a biologist, and he wants to understand the locomotion of these apes. And we're going to try to understand by solving a simple optimization problem, or at least try to simulate some reasonable approximation of the energy optimal way to go from one handhold to the next in this kind of a motion. Okay. Okay, so here's our model. That's the ape now. That is the body. It's a point mass body. And the red stick and the green segment are the arms. So you're imagining the ape like this, and this is the black body, and it's swinging, so it has one arm like this, another arm like this in this configuration, and then it's going over like that. So that's what that's doing. So we would like a motion that perhaps looks like this. And this example is based on work by Mario Gomes, who used to be a student at the lab where I did my PhD. Okay, so you can make up a simple mechanical model of this system. What we are imagining in particular is just some angles, theta 1, theta 2. This point is O, this point is A, this point is B. You're imagining that this point is M2 or M hand. This point is M1 or M body or something. And in this particular problem, do you have a question, Ananda? No? Okay. In this problem, we are imagining that M1 is much bigger than M2 because it's the body and this is the something that represents the arm. Okay. We would like some means for this animal, robot, whatever you want to call it, to move. And the two muscles or motors, whatever you want to call it, are going to be here. One between this quote unquote point mass. It's not really a point mass in this idealization. It's actually something that has, we can imagine that these two links are connected to the center of mass of the body, and really this has infinite inertia, even though represented by a point. And you have torques on either side, which can apply a torque between this object and this segment, and this body and this segment, right? So if you turn on this torque, this thing will rotate about the body. If you turn on this torque, this thing will rotate about the body. You can write the equations of motion, which maybe we'll see briefly. So, yes. Did you have a question? Oh, you had your hand raised. Okay. Okay. So again, let's go about parameterizing this this problem. What could be a reasonable parameterization? One reasonable parameterization would be this thing starting, well, the initial conditions, theta 1, theta 2, theta 1 dot, theta 2 dot. Those are 4 numbers. Another parameter could be a time of swing, and then torques. There are 2 torques, and these 2 torques could be any function of time, right? So they could be any function of time. It's not a constant. It's not 0. It's not a spring. Could be any function of time, let's say. So these are 4 numbers, 1 number, and then infinitely many numbers. So my favorite way of representing a function for these optimization problems happens to be piecewise linear. And there are pros and cons to piecewise linear versus other descriptions. But this is just one description, and all kinds of descriptions would give you a reasonable answer for this particular problem. So you just break up. So you say the torque as a function of time is some piecewise linear function of time, and we don't know what these pieces are, and we would like to solve for these unknowns, capital T at T1, capital T at T2, capital T at T3, and so on. Okay, and we say that we have n grid points. So yeah, so that's just some description of why piecewise linear. There are some technical reasons. One technical reason is that at least some of these optimization problems involving human movement and animal movement, minimizing or maximizing torques or energy subject to constraints at torques and forces, sometimes has very sharp changes in the torque profile or the force profile. And if you have something that, if you try to describe a function, torque function, let's say, but things that look like polynomials and so on, it might be harder to do something drastic in a short space of time without some numerical issues, perhaps. So that's one reason. But you could use polynomials for this problem, and it would work just fine. Okay, so here's the total number of unknowns now. Instead of infinity, it's 5 plus 2n. And our objective function is going to be the integral of torque 1 square plus torque 2 square times dt, where these two are functions of time. You could have, now why would I want to use this cost? It turns out a lot of biomechanics papers happen to use this kind of cost as an approximation of muscle energy cost, but turns out it has no biophysical basis. If people like to just use squares of things because it's mathematically nice and numerically nice. Turns out it's a good model of electric motor power as well. So it actually has some physical basis. If you're building a robot and you want to minimize the electrical power, total electrical work, turns out at least a reasonable approximation of a reasonable class of electric motors is that the cost is torque squared. Something that's actually better for animals, and a better model of animal and human energy cost is integral of, let's say, the absolute value of the mechanical power at each joint. It's actually more like some constant times positive work, some constant times negative work, but let's just say it's absolute value. But immediately alarm bells should go off because absolute value is a non-smooth function. So if you want to minimize this objective function with this non-smooth integrand, you might run into problems if you use F-min-con. In fact, people tried this before and they would get just really bad convergence and so on. So the trick to solving these problems reliably is to pay attention to whether you have non-smoothness in your problem or other things that violate the conditions that your software assumes or the algorithm assumes, right? So these absolute value signs might as well, you do better if you remove these absolute value signs. And one way of removing these absolute value signs without completely changing the cost is to say that the absolute value of a function is approximately equal to square root of, so absolute value of p is going to be approximately equal to the square root of p squared plus epsilon squared, where epsilon is a small number. This is arbitrarily differentiable. This is not at p equal to 0, right? And as epsilon goes to 0, this is going to be equal to this. But when epsilon is small, this is approximately equal to this. These two functions will look identical, except that when p close to 0, this thing will have a smooth curve, and that other thing will have a sharp kink. Okay. So that's smoothing, and that's actually a common strategy that I use to smooth the problems. And then you can actually do meaningful things like try it for 1 epsilon, epsilon by 2, epsilon by 4, epsilon by 6, and see if you can say something meaningful about the convergence. But then you don't want to immediately set epsilon equal to 0. Then your optimization will not converge or give you nonsense and so on. Okay. So anyway, so for our problem, coming back to our problem, we have equality constraints, which are the YB of our 2-segment arm is 0 initially, and then 0 finally. So YB of 0 is 0, YB of t swing is equal to 0. And you say, let's say we want a motion in which all the initial angular velocities are 0. In other words, you're starting from rest, and all the final angular velocities are 0. You're ending at rest, right? It sounds like a maybe an inefficient thing to do, but it's just a problem for now. Right. So you want to design a motion, design torques for starting and ending at the ceiling with 0 velocity. And then you can have inequality constraints that say that the arm that actually swings must start behind your initial handhold and end at the to the front of the initial handhold. So so this just says you start here and end here. You could, in principle, have a motion that starts here and ends here, where this arm is here, right? So you could have a weird motion like that, and we would like to rule that out. And maybe in some situations you don't want to put these kinds of constraints, but in this case, I just happen to want to. And that's it. If you want other properties of the motion, you can add those as constraints, linear, equality, or inequality constraints. Right. So you can assume stride length. So if you say I'm going to assume stride length, so I think I can't remember which version I have right now on my computer, but you cannot specify stride length. It's possible to not specify stride length and just say I want to start and end at the ceiling, and that's my only thing. So stride length need not be there. But if you say, but even if you don't have a stride length, you could say maybe these are just negatives of each other. You're saying, let's say, if the initial point is 0, but that's assuming symmetry, right? You're presupposing symmetry of the solution, which need not be true of the solution. It happens to be true, but need not be, I guess, in general. Yeah.
Videos that you showed,
Right.
they are actually in the video. What was being studied is that as the stride length is varied, how the trajectory is changing.
Right.
So
yeah.
coming from there, that is what. Okay.
Yeah, you can certainly prescribe the stride length as well. Yes. So there is a book about this topic, which is pretty good. I think it's wise. It's called Practical Methods for Optimal Control Using Nonlinear Programming, which recommends methods that are slightly different from what I'm describing right now, but I will describe briefly those methods as well later on. Yes? Yeah, effectively, right. Right, yeah. So it's 1 degree of freedom less.
Okay.
You could have a rigid body with finite moments of inertia with 2 arms sticking out, and then torques. Now you'll have 3 rigid bodies, and you'll have torques between the arm and the central rigid body, this arm and the central rigid body, which would mean that applying a torque here would rotate this rigid body and so on.
And you're not considering any moment of inertia for the hands. I mean,
Right, yeah, that's right, yeah. It's just a point mass at the end. It's just a simple example. So this program, I think, is reasonably well commented. So if you go back and look at it, you can parse it reasonably well. The initial few lines are just defining the parameters, and here we are prescribing the maximum torques at the 2 joints. I'm going to say n grid equals 10, which is the number of linear pieces in the piecewise linear description of the function. So you have about 25 unknowns in this simple thing. At least here it looks like I am specifying the stride length, like Pankaj said, but we'll have to see if in the list of constraints I have it or not. I have versions where I comment that out, but yeah. And here is where we define some initial guess for all the unknowns. So for T swing, theta 1 naught, theta 2 dot, and so on. And let's see. So now, what the structure of the program, if you haven't seen it before, is, so there is, let me go out here. Let's do the objective function and the constraint and the post process. And let me pause this here. I guess there's another pause here. Okay. So the initial motion, the initial guess for the optimal motion happened to be that, right? So it's very far away from what we would like it to be. So let me kill it and say, what do we call it? P input naught, input sub naught, and then add something random to it. Some huge thing. Or maybe that's a really bad thing to do. That might have been a bad thing to do. Let me just do that here. Right, so I just increase the torques to be something random and so on. Of course, you can set it equal to 0, which if you haven't seen it, is a beautiful thing to watch. No, I think we are still on the pause. Maybe it won't run long enough. So that's just a completely passive swing. I just set the torque equal to 0. And if I initialize theta to be -3 or 4, that's the passive motion of a double pendulum, famously chaotic. Anyways, I'll do that forever. In any case, the point of that exercise is to just show that by having different initial conditions at different torques, you can make the thing do whatever you want, is the idea. And then I can't remember exactly how long this is supposed to take. If I run it. What? Try it out? Okay. Okay. So we'll let it run maybe for 30 seconds and see where it goes. So what? The equality constraints are that you start at the ceiling, end at the ceiling, start with initial velocity 0, end at initial velocity 0. Aha, yes. Okay, yeah, good point. Maybe as this thing is running, it looks like it's run off. Oh. Sorry. So that's let me run it from. I have a couple of pauses here which I would like to remove before I show this. Do I have a pause anywhere? Okay. Okay, it doesn't look like it. Okay. Yeah, so let's actually look at this. I think that was a pause with a timed pause, I think, if I was right with it. This is the thing that we're talking about. Yeah. Okay. Yeah. So there are three functions. So this is the objective function, and this is the constraint function. And the objective function, let's just briefly look at its structure. It again has this input, which is P input, which is the thing that we would like to find the correct values for, the optimal values for. And param is just some list of parameters like the mass of the arm, mass of the body, various other things. And this thing, you're just unraveling P input, T swing, the initial conditions, and then what I call AA1 is the set of all torques. T1, the torque number 1, this is torque number 2. You assemble the initial conditions here. You set up options for ODE 45, and then you loop through the piecewise linear, the number of pieces in the piecewise linear function, and then evaluate. That's the place where you evaluate the motion. And having evaluated the motion, you can compute the objective function. In this particular case, the objective function does not really depend on the motion itself because it's just torque square, which is directly known. But for a more complicated objective function, it will depend on the motion. So essentially, the objective function has a little ODE simulation. That's the ODE file, which is this file, which, as usual, has this is where you unwrap all the parameters, and here you essentially get the torques at a given point in time within that little piecewise linear piece, and these are just the equations of motion for a double pendulum. And yeah, yes, not satisfied. That's right. That's right. Yeah. That's the yeah. I mean, there is in some circles a temptation to convert what are naturally constrained optimization problems and turn them into unconstrained optimization problems by some trick. In other words, there is a temptation to reduce the number of variables. That temptation must be resisted, in my opinion. As I will show later, in fact, the optimization problems tend to be more robust, more likely to find solutions from incredibly random initial conditions if you actually increase the number of variables incredibly dramatically, like by a factor of 10 or 20 or 100, rather than decrease it. So, yeah. So to answer your question, yes. So the constraint, the optimization program, the FMINCON only guarantees that the constraint, not guarantees, but works towards the constraints being satisfied at the final step, at convergence, not during the initial intermediate process. Yes. Why is that? Maybe I'll get to this in a few minutes. But the idea is that, I mean, I don't think people understand it deeply, but in a general sense. But I think you could make a problem more linear by adding more variables. If you reduce the number of variables, you're sort of doing something weird and nonlinear. We'll see an example. Actually, maybe this is actually a good example of this phenomenon. Yeah. For this problem, certainly, yeah, absolutely. No, not for this problem. That would be a fine approach for this problem. No, so for this particular problem, that would be certainly a fine approach where you say, I mean, it's easy to parameter, you can say linear interpolant between 0 and 2 pi or so whatever interpolant, so that the position constraints and the velocity constraints even are completely satisfied, and then you can differentiate it to get accelerations, to inverse dynamics to get torques. You can do that. That would be a fine way to do the problem for this particular problem. I'm not saying that intuition is incorrect. I'm just saying the general intuition that smaller number of variables is better than larger number of variables, or having the constraints satisfied always is better than not having them satisfied. That general intuition is, I think, is not well founded. That's all I'm saying. For this problem, it's fine, I think. In fact, that would be way faster, because inverse dynamics is algebraic, forward dynamics is differential equations. But you can do that only for fully actuated problems. If your system is fully actuated, in other words, it has a torque at every joint, you can do inverse dynamics, but you cannot do it for under-actuated systems. Like, if people want to know what I mean, under-actuated systems are mechanical systems which don't have ability to sort of apply torques at each joint. For instance, the human body does not have a muscle that runs between your foot and the ground. So So that giant, you cannot apply a torque between your foot and the ground, I guess, which means that if you're given a motion, that motion need not be consistent with the available torque producing capability. So you'd have to do forward dynamics for that. You would have to specify torques. You'll have to simultaneously solve for torques and motion in that case. Okay, where were we here? Right, so in the objective function there is a little ODE solution. If people haven't seen ODEs for double pendula, so they look somewhat complicated, but not as complicated as what you would write for something that looks like a human body. You would have pages and pages of equations. Maybe I'll flash that just to show off later in the talk. Okay, so and then the constraints also have the same, almost exactly the same structure. The variables are unwrapped here, and then you have this loop that does the piecewise integration for each piece. There is an ODE solution which is done by ODE 45 to a pretty good accuracy, 10 to the minus 9, and so on. And then what we are evaluating here are essentially the endpoint x and the initial x here, and we are saying minus x end should be less than or equal to 0. In other words, x end is greater than or equal to 0. That's an inequality constraint. And x0 should be less than or equal to 0. It's another constraint. And then these are equality constraints here. Theta 1 dot, theta 2 dot, initially and finally. Of course, some of these are linear constraints, right? So because linear constraints of your unknowns, for instance, theta 1 dot and theta 2 dot are part of your p input, part of your initial set of unknowns. So you could just make them equal to 0 or set the lower bound and upper bound of those variables equal to 0, making that an equality constraint as well. So there are lots of ways to tell MATLAB or whatever software that you use that those are actually simpler constraints than nonlinear, right? So you would actually save time if you did that, but you can be lazy here and just say these are pretend that these are nonlinear constraints that you'll have to give it into the constraint function. I don't like pause. It looks like I didn't cheat enough in setting up the initial conditions. Doesn't look like it's making a lot of progress here. So I think it runs for a while before it finds the optimum. I don't know if you can wait for it. Looks like, so I cheated a little bit. I had initial conditions. Well, initial conditions certainly at which the constraints were violated, right? So at least one of the equality or inequality constraints is, or the sum total of all of them is 2 away from where they should be. And notice that as MATLAB progresses, the constraint satisfaction goes to 10 to the minus 8 now and so on. Is it actually done? Okay, it keeps going, but the idea is that right now the constraints are satisfied to 1 e minus 10, which is pretty good. I guess it's running now. I don't know if people saw that animation, but it looks like it's at least satisfying all the constraints pretty well. It's probably pretty close to optimal now, but the problem is, oh, it looks like it's done. Okay. Okay. What is the post process? Okay. So you probably noticed that I cheated a little bit in that I'm touting this method, but what I was forced to do, so I had tried to make the initial conditions different from what they were initially, just to demonstrate different kinds of motions. And when I started the optimization from my sort of final initial condition, so to speak, it ran away and wasn't making as much progress as I was hoping, because I wanted the optimization to finish. Maybe it would have ran for a couple of hours and gotten somewhere, but certainly it would not have finished in the 30 seconds it did, right? So depending on your initial guess, some of these problems can take a minute or an hour, depending on how lucky you are, right? Sometimes it will never converge, just because these are highly nonlinear problems. For instance, if you gave it an initial guess for the total time on the order of 20 instead of whatever it happens to be, what is the actual answer? Let's see what the actual answer is. If I type p result, the first element, which is the time of swing, is 1.36. I happen to give 1 instead of 1.36. And had I given 10 or 20, it would have taken a long time, or never converged, or converged to some other weird looking solution that spins around a few times and then got to the ceiling. So that can happen. Oops, what am I doing? Okay, any questions? For some problems, multiple solutions exist. Yeah, for this problem, I would say if you gave this problem angle bounds, right? If you said the angle between this upper body and the arm is constrained to be physiological only between this and this, then I haven't done work in this particular problem. It's just something that I made up for this tutorial. My guess is that does not have multiple solutions. But if you let it spin around 3 times or 4 times or 20 times, then my guess is this does have multiple solutions, probably infinitely many solutions. Countable infinity of solutions is my guess. Right, then you would have no solution. Yeah, so let's actually see if the stride length. Right, yeah. What do you mean by those will not be captured? Oh, in the actual, in the video, in the original video, I see. In the actual, in the real video. That's right. Yeah. So this, but okay. Let's actually talk about that. That's a good question. This optimization problem assumes that the first handhold is always on, and then this thing is swinging over, and then the second thing and then it approaches with 0 velocity, and then the second thing catches, and so on. But we just simulate until the second. the second arm reaches the ceiling. But let's say you want to simulate or get the optimal motion for that does have a flight phase. What you would do is relatively simple extension of what we just saw. What you would do is have two phases to the motion. The first phase being having the hand hold on, and the second phase pure flight, and you would write a different set of differential equations for that second flight phase. And for the first flight phase, you have torque as a function of time, tau2 as a function of time, and then maybe the time duration for the first flight phase. For the first phase, similarly, you have the same set of variables for the second flight phase. You could have initial conditions for the second flight phase, the time of swing, the torque as functions of time, and then you can try to optimize for this larger set of variables, and you would have additional constraints that patches these two things together if you have initial conditions as one of the variables for the second flight phase. So there is a temptation, for instance, to use the final condition of the first phase as the initial condition for the second phase. But if you're simulating a big, a large number of things, doing a very long simulation is a bad idea if you have a very nonlinear system, because if you get the initial guess for the motion wrong, you're just going to be in a very weird part of your solution space, and the optimization might never recover from that. So what you want are local tweaks, local control of the variables. So I'll actually talk about that, but that's an example where you want more variables rather than less. Okay. So I guess we just saw that work. The method that we just saw is called single shooting. And the word shooting is inspired by, I think, the so-called shooting problem, which is the first problem that I described, more or less the first problem, trying to hit someone from far away. And it turns out for very nonlinear problems, a double pendulum is nonlinear enough, but if you have the human body or something that has lots of degrees of freedom, if you give it the wrong torque as a function of time, so you start from some initial condition, let's say for something like that looks like a human body, and then run it forward with your initial guess for the torques as a function of time, the resulting motion will probably end up on the floor incredibly fast, because it's an unstable system. It takes considerable sophistication to stabilize it, and if you just randomly guess torques, the resulting motion would just be absolutely crazy, right? Which means that you're going to be very, very far away from your initial solution, and it might be very hard, and then even satisfying the constraints, and be very hard for the optimizer to get back to first satisfying all the constraints and then optimizing them. Let me back up a little bit. The theoretical guarantee for this class of optimization methods is that you have all these nonlinear constraints, equality, inequality constraints, and then you have this nonlinear objective function. The approximate theoretical guarantee is something called global convergence, by which really they mean local convergence to local minima from points that are already feasible. In other words, if you give it a point that actually satisfies all the constraints, then you're able to go to some local minimum of the problem that satisfies the constraints with some convergence rate and so on. But if you start from somewhere, for a general nonlinear problem, there is no guarantee that the constraints can be satisfied eventually. But these optimization problems are pretty good at trying to find feasible solutions. By feasible, I mean solutions that satisfy all the constraints. In any case, if you do single shooting, in other words, you have a nonlinear dynamical system and then you're simulating it for a very long time with lots of torque pieces whose correct values you don't really know initially, so you're just guessing at random or guessing with some informed information perhaps. you're likely to run into trouble. Turns out there is a better method, and this is the method that I mentioned, increases the number of variables dramatically. Right? So it's called multiple shooting. People that do boundary value problems, let's say univariate boundary value problems, might be very familiar with this. The idea is straightforward. The idea is that you break up the total time into multiple pieces. You have unknown initial state at the beginning of each of these pieces. You might not have just 4, you might have 20 or 100. But each segment has an unknown initial state, and each segment has some unknown, in our problem, torque as a function of time. So initial state is unknown, torque as a function of time is unknown, and if you simulate starting from this initial state with this torque as a function of time, you might get some motion that looks like this. This is the initial state for this segment, and if you simulate with some torque as a function of time, you'll get here, and so on and so forth. So you have lots of little pieces of motion, and at the interfaces they are not matching up, but eventually we would like a physical motion that is continuous and differentiable and so on. So you have all these unknowns, and then you have additional constraints, which would be essentially minimizing these defects. In other words, this point needs to be this point must be identical to this point, and then the slopes must match and so on. So that's the idea. So you're increasing the number of variables by a factor of 10 or 20, depending on how many segments you're using, 10 or 20, and then trying to see what the optimal solution is, making sure that the thing is smooth. And so that's called multiple shooting. And a very closely related thing is called direct collocation, where essentially you have an incredibly large number of pieces, if you will, and each segment has really just one ODE step or one expression of the fact that the ODE needs to be satisfied. Yeah. In other words, each point, let's say you break up the whole motion into 200 points, and each point you have the states are unknown, the controls, namely the torques in this particular problem, are unknown, and then you say the states, the appropriate states derivatives must be equal to the torque, blah blah blah. In other words, you write an equation that expresses the differential equation in terms of these unknowns. That's your constraint. You have essentially a lot of differential equation constraints. That's direct collocation, and then you add other constraints that express your particular problem. Again, this is a problem in which the number of variables is very large, but in terms of convergence from random initial conditions, this method or multiple shooting is vastly better for substantially nonlinear problems than single shooting. Like for something like walking, unless you're almost on the correct walking motion, there's no hope of getting a good walking motion. On the other hand, for my walking simulations with like the lot of muscles and so on that I showed out here, for this model, I can actually use random number generator for the initial seeds, and things zoom in to something that is reliable and so on, because I'm using this method called multiple shooting rather than single shooting. Initially, this object is going through the floor, flying through the air. None of the constraints are satisfied. Even the physics is not satisfied because the differential equations are not satisfied. So it's crazy initially, but then there are these thousands of constraints which make sure that the joints can't hyperextend and so on and so forth. And the constraints are satisfied better and better over maybe 5 minutes or 2 hours. Eventually you get motions that look continuous, differentiable, and minimize energy. And if you run the optimization from 2 random initial conditions, for at least some of these problems, we get the same answer from to up to about 3 or 4 decimal places. So it is possible to be robust and so on. So lots of resources. There are canned softwares to do the transcription. So I sort of wrote this my own code where we integrate the differential equation piece by piece and putting all the constraints together. There are some softwares that try to do it for you. In other words, if you express your constraints and express your differential equations in some standard manner, they will put together this transcription of your optimization problem and then send it to us optimization software, and then give you back solutions. I don't know why I haven't used them, but I just feel like I would like more control over the transcription. So these are some I think these are all paid software of some sort. I'm not sure. So so I just described these methods for solving optimization problems. Now, why not use something analytical? Why do we want to succumb to numerical optimization? This is a question that I used to be asked about 10 years ago. People ask that less now. And the analytical approach would be the following. I don't know, many of you are probably familiar with the Euler-Lagrange equations for the minimization of a function of functions, which appears in various mechanics fields. So where look for a blackboard. It's okay. Where essentially you have the integral of some function of, let's say, x and x dot and t or something like that, dt. So that's a simple functional optimization problem. The kind of optimization problems that we have the following form: integral f of x comma x dot comma u, where u is some other function like the torque and so on, dt. So that's the function that we want to minimize. And then we have a whole bunch of constraints. X of 5 is greater than this, x of 6 is greater than 7, something like that. And then u can be bounded various ways. And then there might be weird nonlinear constraints involving x and so on. So there's lots of different constraints. If you don't have too many of these constraints, there is a form, and then x dot and u have to satisfy the governing differential equations. In other words, you have a functional optimization problem with differential equation constraints and perhaps a whole bunch of what we call state constraints and control constraints. Euler-Lagrange equations does not have all those constraints in the formulation. But in the 1950s, lots of control theorists generalized the Euler-Lagrange equations to what is now called Pontryagin maximum principle and minimum principle, and then generalizations thereof, which have the Euler-Lagrange equations as special cases. But you can use these principles on the optimization problem, and then you'll get a bunch of conditions that need to be satisfied. The problem is that these conditions take the form of what are called two-point boundary value problems, and they are a little bit harder than solving the optimization problem directly by discretizing, I would say, especially because these differential equations tend to be unstable. You'll have to simulate them and then solve the boundary value problem. It's almost as hard as the optimization problem, and it turns out in practice the optimization problem is actually easier. So that's why we don't try to do analytical stuff. What I mean by analytical stuff, by the way, is the equivalent of saying, if you want to minimize f of x, set df by dx equal to 0. That's what I mean by analytical. And then those are the necessary conditions for optimality. This is the equivalent of df by dx equal to 0 in this infinite dimensional context. So I have promoted this class of smooth methods. In other words, things that assume twice differentiability. So if you have an optimization problem that does have non-smoothness, you have to contort it to be smooth. Smooth methods tend to be vastly faster than non-smooth methods. In other words, the more you can assume about the problem, the more structure there is in your problem, the better your program can be potentially. But of course, if what you assume is not true of your problem, then you're digging a hole for yourself. There's a whole class of other methods which don't necessarily use all the structure perhaps. Sometimes there are hybrid methods that do use. These methods only find local minima, but the hope is that you can start your optimization problem from lots of initial conditions and make sure that the optimum that you find is in fact the global one or something like that. There's other methods that try to do this for you in some reasonably methodical way. I won't talk about those, but you can look it up. There is something else more recently that seemed to be popular, which I haven't written down here. It's called covariance matrix adaptation, which is sort of related to these methods, which for some reason the last couple of years has become popular in the computer science literature, which tries to do something reasonable for non-convex problems to find global minima. If your function is really horrible and you can't assume differentiability, you might try to use some methods that don't assume differentiability, I guess. But these would be really slow, right? So, I mean, the kinds of problems that we are trying to solve have thousands of variables, but if you're not using differentiability and so on, they're going to be much slower and probably not practical for many thousands of variables. There are some tricks here. We use lower bound, upper bound, Nefman Khan, and all these softwares come with lower bound, upper bound as well. Sometimes there are values for your inputs for which the evaluation of your objective or constraints or even your motion can be meaningless. For instance, time cannot be negative. It can be, but that's not a big problem. But there are some situations where maybe if you simulate for too long, you hit a singularity in your problem or something. Maybe you want to be bounded away from it. And if you can express that as a simple bound on the variables and the optimization respects that simple bound every step, that's a good thing because you don't want the optimizer to crash the evaluation, the function evaluation. If you think if it does, then you want to make sure that it doesn't, I guess. And this is what I said, it assumes second derivative, so you want to make sure you do satisfy that assumption. Right, so like people say, oh, I find lots of local minima. Of course, sometimes there are lots of local minima, but sometimes there might be non-smoothness in your problem, and because these algorithms assume smoothness, they might get fooled if at a point of non-differentiability, for instance, and just stop there and claim optimum. So you can't trust it. Something that I avoid in these problems, you asked about things that have different phases, a hold phase and a flight phase. For something that looks like walking, there are lots of phases as well. For instance, in human walking, here this foot is on the ground, and then this foot hits the ground, this foot takes off, and so on. And when human running, you have foot on the ground, no feet on the ground, and so on. So there are lots of different phases. There is a temptation to do the following thing. It's a very natural thing to do, which is to say, let me describe the torque as a function of time for the whole period, for the whole motion, from the beginning to the end, through all these little transitions between phases. And then what you would do is you would simulate forward in time, detect an event, change the equations of motion, and simulate that set of equations of motion, and so on. Detecting events in the optimization calculation can lead to problems because it lowers the accuracy of your function evaluation, for instance. Because the event detection typically has a root find in it, and if the root find is not as accurate as your differential equation evaluation, you're lowering your function evaluation accuracy, and so on. Sometimes these event detection approach can also mean introducing non-smoothness into the problem. For instance, if you have this piecewise linear thing and the event, depending on your function, depending on your particular function, sort of transitions from one piece to the next, then that might be a kink in your objective function. Again, right, so what I tend to do is assume a structure. In other words, that is a single stance phase when this foot is on the ground, and then when this foot is on the ground, and so on. So I assume different phases, and then I have separate functions for these two phases. I don't assume that I'm going to detect this event. Rather, I have initial conditions for the beginning of this phase. I evaluate the final conditions for this phase, and then make sure that I have an equality constraint that patches them together, rather than trying to do event detection. In other words, we increase the number of variables again and add extra constraints, just to make the problem smooth, right? And there are other benefits as well to doing this. One big problem in these optimization calculations is the quality of the derivatives, especially if you're using something like F-min-con. If your derivative quality is horrible, the optimizations results are unreliable. It will say converge when it's not converged, or it won't converge at all, or just sort of bounce around in the noise. And there are lots of different ways of making sure that you have good derivatives. The best way perhaps is something called automatic differentiation, which maybe if you're interested in, you should look up, which essentially takes your program and constructs another program to find the derivative, right? So it's an automatic way of figuring out what the dependencies between the variables are and how they are related in terms of what operations relate them, and then getting the derivatives as accurately as the actual function evaluation. So that's automatic differentiation. It's also called algorithmic differentiation. So that's the gold standard. It's incredibly efficient as well. But the simple thing that everyone does is finite differencing. In other words, you evaluate the function at 2 points, take divided differences. But you have to be really careful in picking the size of that step for derivatives. For instance, in this case, I just let F-min-con do it. Yeah. In this example, in my own for the big optimization calculation, I find the derivatives. I happen to find the derivatives, but well, actually, the second derivative is approximated from the sequence of first derivatives by the optimization program. There are ways of this classic ways of if you have a sequence of gradients. The most famous one is called BFGS for some sequence of people. But yeah, essentially, it updates its knowledge of the second derivative based on sequence of first derivative information. So it has this. Right. So you don't want to be. Almost no one sits around and compute the full Hessian matrix and then move forward. That is never done. Rather, only first order information is explicitly calculated each step, and then the second derivative information is updated starting from identity matrix or something like that. Right. So coming back to finite differencing, right. So we said that the differential equation, if you notice in my program, I set a tolerance 10 to the minus 9, which roughly is going to be the level at which there is numerical noise for ODE 45. In other words, at the level of 10 to the minus 9, you cannot trust ODE 45 solution to be continuous and differentiable and so on for small changes in parameters, because ODE 45 does what's called adaptive stepping, which in other words, it adjusts its step based on how accurate it thinks the solution is. And if you change the initial condition, say slightly, it might take a slightly different sequence of steps because some if-then statement got triggered. So in other words, at the level of 10 to the minus 9, ODE 45 based evaluations are not continuous, not differentiable, and so on potentially. So so there is essentially noise at the level of 10 to the minus 9, which means that if you take a finite difference step that is too small, let's say at the level of 10 to the minus 9, you're differentiating noise, you're getting nonsense. So really you should take, if you're doing forward difference, it should be about 10 to the minus 4.5. If you're doing central difference, you need something else, 10 to the minus 3 or something for the step size. You can certainly do that. I guess it depends on the differential equation if it can give you more than 10 to the minus 9. It depends completely on if the differential equation is particularly horrible, it might not be able to satisfy. I don't know what the limitations are, but you can certainly ask for it, and you can check if it's satisfying a higher tolerance. But I didn't quite write the write the relationship here. But if your function evaluation is accurate to, say, epsilon, you want square root of epsilon for the finite difference step size. If you're using forward difference, if you're using central difference, it's epsilon power 1/3 roughly. There's another caveat here, which is I used ODE 45, which is MATLAB's ordinary differential equation solver, to do the ordinary differential equation solution. The usual advantage of ODE 45 is that it does adaptive step sizing, so that if you ask for a particular accuracy, like 10 to the minus 9, it can adjust its step size to give you roughly that accuracy. Alternatively, you could use constant step size, say Rangekuta, for the same problem. If you use constant step size Rangekuta, let's say it takes 1,000 steps to get a really good solution at the level of 10 to the minus 9, and let's say you do 100-step Rangekuta, which is maybe only accurate to, I don't know, it's going to be 10 to the minus 4 or something, right? You will find that if you use the constant step size Rangekuta with only 100 steps in the optimization program, and you'll find that the optimization perhaps converges way more nicely. This is because even though it is less accurate, it is a smoother function, because it takes the same sequence of 100 steps. There is not this adaptive step sizing. So even though it is accurate only up to 10 to the minus 4, it is what is called consistent to essentially, right? The level of numerical noise will be at the level of round off 10 to the minus 14 or something if you do a 100-step Rangekuta rather than a 100-step adaptive step size thing, right? So very often for these problems, if you can back off on accuracy, if your problem is not pathological and you can simulate it without it blowing up with a lower accuracy but constant step size solver, you can use a smaller finite difference step size, which will give you much better derivative estimation and so on. So there are all these weird tricks. Oh, so it looks like I have it here. I just mentioned that square root of function and function evaluation. I just said that. And I guess this is similar to what Anindo suggested initially. The alternate parameterization for shooting. You could, instead of parameterizing the torques, you could parameterize theta double dot, for instance, or theta, of course, but theta double dot differentiated to get theta dot and theta and so on. And this is sort of an answer to Ishan's question. Doing this multiple shooting or direct collocation does make the problem much bigger by factors of perhaps 10 or 100. But I think the intuition is that they make the problem more linear. There are many more constraints, but nothing changes dramatically when you have, right? So when you have one initial condition and a long simulation, they call this the wagging the elephant by the tail problem. It just gives you weird things. Potentially, it can go unstable and give you very large changes in the final state for small changes in the initial state. But when you break it up into lots of pieces, what happens is small changes in the initial state, because you're simulating only for a small amount of time, only means small changes in the final state for that piece, and then you have local control for each piece. So all these lots of constraints, even though they're officially nonlinear, are sort of more linear, and you can make progress very nicely. I guess that's the end of this presentation. myself, fmin_con in particular, or other optimization problems? Others. Okay. So fmin_con maybe I can't remember if I've tried to push fmin_con to really large problems. I switched at some point, but maybe 60, 100 successfully. Of course, all this depends on how weird the problem is, and that is that caveat. For Snopt, which is the other program that I use, I've gone up to a few thousand unknowns, and it converges reasonably. I think 300 or so. Yeah. Something that I forgot to mention is in, I guess it's in the other. I briefly mentioned this in my talk for a couple of days ago. I'm pointing to this now. So we mentioned this multiple shooting method, which increases the size of the problem dramatically, right, from maybe 100 to 2,000 by increasing the number of segments. But the problem secretly is not as big as just the number might seem to suggest, because this constraint that says these two things have to match really depends on only variables that correspond to this segment and this segment, right? So this constraint has non-zero derivatives only with respect to these two variables, will have zero derivatives with respect to these variables and those variables. So the Jacobian for various constraints and various objective functions for these large problems that arise from, say, multiple shooting are incredibly sparse, right? So this is the Hessian, it turns out, for some optimization problem for that person, and each block is essentially the variables that correspond to one little piece of multiple shooting, yeah, so it's very sparse. There's a very small number of non-zero elements. Similarly, these are the constraints, which means that so the S in Snopt stands for sparse nonlinear optimization or something like that, and it takes advantage of the sparsity to do smart things that I don't know anything about. Yeah. At those interfaces, right? I would say that's not true. That's what I'm saying is not necessarily true. It depends on the problem. There are some ways like this of increasing the size of the problem that actually makes the problem easier, not harder. In fact, the larger you make it, the easier it gets up to a point. Yeah.
Trajectory, all constraints satisfied, and then we increase the number of points to 10.
Right.
And we get, obviously, not obviously, but if at some points it's not satisfied, then the previous trajectory which we got, is that, should it be rejected or it's correct?
I'm not sure if I completely.
When I'm specifying the angles, because I have a fully actuated system, that's exactly what he's trying to do. And he's calculating the torque. Now, let's say we put a limit on the maximum torque. Now, we only check it at a certain number of points. We don't sort of interpolate again and find the maximum. We don't do that.
Okay, go ahead. Yeah.
Is it all right to just check at a discrete number of points? I'm happy with that.
Right. So that's what I do as well. Yeah. So there are various nonlinear constraints. For instance, the fact that these angles cannot exceed a certain value, and I check that only at a discrete number of points. But let me make another comment. Again, that might be if that variable change is a function of time is expressed, say, by a quadratic or cubic or something like that. Let's say a quadratic. There could be a temptation to find the maximum and then apply a constraint on that. Again, that temptation needs to be resisted because the maximum of a function is a non-smooth function of the function. Because for if you have 3 or 4 points, let me just expand on this. If you have 3 points, what's the maximum of those 3 points? It's whatever the maximum is. Imagine 2 points exactly at the same height. As you change the height of these 2 points, this point becomes the maximum or this point becomes the maximum. So they change dramatically, in fact non-smoothly. So the maximum of a function is non-smooth. So you don't want to take the maximum. Yeah, what you're doing is actually the right thing to do, or the better thing to do for problems like this to work nicely.
Or if you are using a B-spline kind of representation, then you don't have to worry about intermediate work, because your representation of the points will be these points, and because of the conventional property, everything is guaranteed to be within. So if you ensure that these points are within your maximum, everything else will always be within.
Right. Especially Bezier curves, right? Right. So you can do that. I found I tried that. It did not. It seemed too conservative. The convex hull property. So I don't know if I tried B-splines, but the convex hull property of the Bezier. Okay. There is this class of polynomials, polynomial representation called Bezier, something or the other, are closely related, and they have some property that if certain things are less than 0, it doesn't exceed something. So they have this boundedness naturally built into them. But just saying those things are less than 0 turned out to make so many of these solutions. Okay, I see.
We have used it in some place and we have
I see. Maybe this is a longer conversation. But I tried some version of this, and what happened is that it doesn't want to go and hang out at the maximum. It turned out that we needed greater discretization for it to hug the maximum, so to speak. But yeah.
By increasing the number of these bases, you are increasing the size of the problem and you are increasing the number of constraints. But now the space in which you can move around to get to the final space also increases.
Right.
So you get better options to move and try to get to the best solution.
That's part of the intuition, I think. Right.
Want that it should always be on that surface where the solution is, for example. The final point, the optimum point, you want it to be visible.
Right. Right.
Here is the question I had in mind. Let's say I've specified that the angles are my design variables. Using those and inverse dynamics, I find the torques. I actually have limits on the torques. So I could write those limits as these nonlinear functions of the angles. Or I could introduce torques as other variables, put limits on them, and have equality constraints between the torque and this computed quantity.
Right.
It seems to me that the two are exactly equivalent, but
Probably not in practice.
so what are the implications in your opinion?
I have to say this is a job for experiment. You have to try it and see, I think. But that happens to be what I do, the latter thing. In other words, I have torque unknowns as well as angle unknowns at each point, and then have differential equation constraints relating the two. So it's a larger problem. And in my experience, which has not been systematic, checks and so on for large class of problems, but in some class of problems I found the latter to be better. But I don't have a proof for even systematic tests. Did he have a question? So so another, by the way, useful aspect of the fact that these problems are very sparse is that the Jacobians can be computed very efficiently. Even though it's a 1000 by 1000 matrix, only a few are non-zero. So if you know which ones are non-zero, it turns out you can compute them very efficiently. Instead of doing 1000 evaluations, you might just have to do 200 or something like that. What do you mean by that? Right, they don't compute the Hessian. That's right. Yeah. So if you know the sparsity structure of the Jacobian based on your knowledge of the dependencies, you can give it to these solvers, and they will evaluate the the Jacobian, the Hessian, more efficiently if such efficiency is to be had. How are we doing on time? 1.5 2 hours? Oh, pretty much, yeah. Say it again? Okay, I see. So the only other thing that maybe I could briefly talk about, but I think we've already talked about this. I was actually going to show the programs for this particular problem, but maybe I'll just describe it in words. This is actually this problem that I described yesterday, and really those are the equations of motion. The model can be in one of two states. Either the leg can be on the ground or off the ground. When it's on the ground, it's able to produce some force on the upper body, like so. And these are the differential equations, really simple differential equations, freshman physics. Mx double dot equals force on it, F times cosine theta, F times sine theta minus mg. So really simple differential equations during what we call stance phase, really simple differential equations during flight phase. And this is a problem in which there are two phases potentially. You simulate the first phase, simulate the second phase, and make sure they patch up together and so on. It's actually a slight variant of this problem. I'm maybe just going to run this and see if people have any questions. So this is actually simulation of two steps, and the initial condition is it's not satisfying these continuity constraints and so on. And as the thing runs, you'll see that it gets better and better. This is actually two stance phases. There are no flight phases allowed, so we're solving the problem that I described yesterday in real time, I guess. It doesn't take all that much time. I think it just takes maybe 5 minutes or so. Any questions? Thank you.